6, Section 5, the average value of a function. I'm your host, Dr. D. All right, the average value of a function. Now, a function is a y value, basically. So we're looking for the average height of our function. Now, let's first take a function that has the same height all the way through. So f of x equals some constant. Now we're going to start from point A and end up at point B. So that means our area here is going to be base times height, which is b minus a, the length of the base, times c, which is the height. Now, if I want the average value of this function, then what I would do is I would just divide out the base. And that gives me height alone. So height, or the c, is going to equal 1 over b minus a times area. So area equals base times height. If you want the height, you just divide out the base. All right, now, let's look at a function that's not constant then. So what we're looking for is the average height between a and b of this function. So it starts out high, goes up a little higher, then goes down low, and then starts back up a little bit. What's the average height in between there? That's the average value of the function. Well, we're going to do it the exact same way. We're going to say the height equals the area divided by the base. That's all there is to this formula. So you just go 1 over b minus a times the integral from a to b of f of x dx. So area divided by base equals the height. All right, so let's try an example problem with that. Here we have our function f of x equals 1 plus x squared. And we want to know the average value of this function between x equals -1 and x equals 2. So what is the average value, or in other words, what's the average height of all the vertical lines from -1 up to 2? Now notice the height at -1 is 2, the height at 0 is 1, the height at 1 is 2, the height at 2 is 5. We want an average height from -1 to 2. So we just plug in the formula. So we say f average is going to equal 1 over b minus a times the integral from a to b of f of x dx. All right, so that's going to equal 1 over b minus a, that's 2 minus -1, times the integral from -1 to 2 of 1 plus x squared dx. So notice we're just taking the area and dividing by 3, because that's the base, area divided by base. So this becomes 1/3. Now I'm going to perform the integral here, so this is going to be x plus x cubed over 3 from -1 to 2. All right, so this becomes 1/3 times, I'm going to put my 2 in here now, so it's going to be 2 plus 2 cubed over 3 is 8/3, minus, put my -1 in here now, so -1 plus -1 cubed over 3. So this becomes 1/3 times 2 plus 8/3. Well, that's 6/3 plus 8/3 is 14/3. Now, minus a -4/3. So this is going to be plus 4/3. Okay, so this ends up being 18/3, which is 6. 6 times 1/3 is 2. So we see that the average value of this function is 2. Now, where does that occur? Well, let's talk about that later. Basically, that's it. The average value is 2, and that's all we're interested in right now. Okay. So, cruising onward, we have the mean value theorem for integrals. The mean value theorem says that if f is continuous on some interval, some closed interval a to b, then there exists a number, x equals c, in that interval such that f of c will be the average value of the function, which is 1/p-8 times the integral from a to b of f of x dx. So, what that's saying is, here's our function again, and I've got point A at the beginning, point B at the end. Now, somewhere in between A and B, there has to be an average value. All right, now, it took me a whole bunch of times to do this, because when you do it and then you check it out, you can see it doesn't work if you didn't do it exactly right. But notice I estimated that this point right here gives me my average value between A and B. Now, here's how you check that. Is basically what we're saying is, if I take my average value C, then I'm saying from A to B, the average value of this function is this level right here at C, f of c. So what that means is the area under the curve has to equal the area of this rectangle. Now what that means is this rectangle has a piece of area above it. So that's the amount we added to the rectangle. So if we did this right, then this area below it that we're taking out of the rectangle should be equal to that. And we need to put that in yellow, of course. So this area if I did it right, which obviously I did, the green and the yellow are exactly the same area. Notice what we're saying. Let's go over this again. C is the x value where the average value of the function occurs. So that means if I draw a line up from C to the function, then that level becomes the average value of the entire function between A and B. Now, the function goes above the rectangle, so the green area is area added to the rectangle, and then the function goes below the rectangle, so the yellow area here is the area taken away from the rectangle, and if you did it right, the green and the yellow are exactly the same area. Now, they're not the same shape, which makes it difficult to tell the same area. It's like when I was a kid and I was splitting a cookie or something with my brother. My dad always said, you divide it and then your brother can choose which one he wants. So I figured, well, if I divide it where it's right down the middle and I mess up just a little bit, then he's going to see right away and he's going to take the bigger part of the cookie. But if I divide the cookie in such a way, like kind of curve it around and move it back, then he's going to sit there all day wondering which side of the cookie is actually the biggest. And I have a 50-50 shot at getting the bigger half of the cookie. See how math comes in handy? Okay, so back to the ranch. Now what we're going to do is we're going to go back to the example problem that we just did here, and we're going to say, where is the c value that we're promised. So we found out that the average value of this function is 2. Now, the mean value theorem for integrals says that somewhere in between x equals -1 and x equals 2 will be an x value where we have a height of 2. So notice the first place I see is right here at -1. That's a height of 2. The second place I see is also, well, it's right here at x equals +1. So x equals -1, x equals +1 are both points where the c value gives us an f of c that's the average value of the function. So, okay, if you wanted to do that algebraically, then what we do is we go f of c, we know equals f of average. So f of c equals 2. Because we found out that's the average value of this function. Now, what that says is then, f of c is 1 plus c squared. Because that's my function, 1 plus x squared. All right, so now I just need to solve for c. So subtract 1 from both sides, and c squared equals 1. And so c equals plus or minus 1, which is exactly what I just found out, geometrically. So this is how you do it then. To get the average value of the function, you just go 1 over b minus a times the integral of the function from a to b, and you get that average value. Then what you do is you set that equal to f of c, which is going to be your function with c in it, and then you solve for c. So notice we got the average value of the function, and we got the x value where that occurs, and the mean value theorem for integrals states that you're guaranteed at least one of those values. Okay, cruising onward. Now, what we want to do here is show that the average velocity of a car on a trip is the same as the average of all its velocities during the entire trip. So we're basically proving the mean value theorem for integrals on this car trip. So the average velocity of a car is the change in displacement divided by the change in time. That's average velocity. Now, what that means is we're going to say it's s at time 2 minus s at time 1. So it's the position at time 2 minus the position at time 1 divided by time 2 minus time 1. That's my average velocity, and we were doing that back in Algebra 1. So now, the average of all its velocities. So this is going to take some calculus. So we say the average of all its velocities. Yeah, we'll do this in blue now. One over b minus a. Well, b is time 2 and a is time 1. times the integral from time 1 to time 2 of the velocity function dt. Now this equals 1 over t2 minus t1, integral from t1 to t2. Now we know velocity is the derivative of displacement. So, the integral of the derivative is the original function with the limits of integration. So we have 1 over t2 minus t1 times s at t sub 2 minus s at t sub 1. Well, notice that's the same thing that we got when we just did change in displacement over change in time. That's it, QED. Have fun with these.